Hey folks, so we're talking about elastic or spring potential energy. I'm going to refer to it as elastic potential energy to the best of my abilities, just because it encompasses so much more than just springs. We base it off springs, but Hooke's law and everything that we associate it with springs really is a model for many types of elastic interactions, even down to molecule interactions, talking about bulk atom to atom interactions. That's actually an Einsteinian model for solids, and it works fairly well, especially when talking about diffusion of thermal energy in basic models. So anyways, a bit of a tangent there, but we're going to talk about elastic potential energy. We've already talked about the work done by springs, so that's actually where I want to start, because when we think about the delta UE, which is our elastic potential energy, it's going to be equal to the negative work done by a spring, right? This is our interaction force, right, our interaction work here. So negative work done by a spring. Well, negative work done by a spring is, work done by a spring is already negative. So it's negative 1/2 K delta X F squared minus 1/2 K delta XI squared. And then we close the parenthesis and then close the bracket. All right. So a few things. One, we have a negative, that cancels. I'm left with the positive. And the other thing is this delta XF and delta XI, which are both squared. We said in the past that this delta X represents the displacement from equilibrium, right? So for a spring, we have an equilibrium length when everything is relaxed and there are no forces from or on the spring. There's no restorative force from the spring when it's at its equilibrium length. Now, when we deviate from the equilibrium length, when we stretch it, right, there's a restorative force inward. When we push on it, right, there's a restorative force outward. And so this delta X is showing the distance, the displacement from my equilibrium length, right? So what I'd like to actually say here is that our potential energy, right, our UE, is going to be 0 at x equals 0, right, at our equilibrium length, right? And so if I think about it this way, I could really just talk about x, right? If I'm saying x equilibrium is 0, maybe a better way of talking about this is really just 1/2 kx squared, right? And then I have a final and initial, right? So final minus 1/2 kx initial squared. I've dropped the deltas. The deltas, again, we're just trying to show a displacement. It's that it was a displacement past equilibrium. But if we put an actual axis on that length, on that position, and say that position is 0, right? I can kind of just drop the delta. The positive, so negative cancels, and I'm left with this business for my negative work done by the spring. Another way of writing that would be the delta of this, or maybe I could say 1/2 K delta x squared. So we put the delta back in, but this delta now means something slightly different. Instead of a displacement quantity that it's representing, it's now representing an actual difference. All right. So just be careful. Make sure you actually are paying attention to what you mean by the delta when you say this. But this is it, right? The change in our elastic potential energy is equal to 1/2 K delta x squared. Where delta x is that change in displacement past our equilibrium. So if I compress it, I store potential energy. If I extend it, right, I store potential energy, right? In either scenario, I have more potential energy than if I were just at equilibrium. So this is a very interesting type of potential energy. It's a little bit different than gravitational because gravitational does have that kind of directional aspect to it. This one doesn't. This one says no matter how I displace past my equilibrium, as long as I'm not at equilibrium, I've stored some potential energy. So we have all our potential energies that we're going to talk about in this class. When we talk about total mechanical energy, right, our change in mechanical energy, we said that that was equal to change in kinetic energy plus our change in potential energies, right? What we actually mean is that there's a change in kinetic energy plus change in all our potential energies, our gravitational potential energy and our elastic potential energy. Now, there are other potential energies. I do want to put that caveat out there. There's chemical potential energy, right? That is not something that we're covering in this class, but it does exist. There are other types of potential energy, but these are the two that we're going to talk about in this class. So that is springs in a nutshell. I want to talk next time about how we can relate this to force. Since potential energy is so closely related to work, it's not going to be hard to show that potential energy and forces are really interconnected as well. And we're going to talk about equilibrium positions in that next episode, next lecture. I don't know why this chapter I keep saying episode, as if I'm some sort of streamer or anywho. It's a little bit too early. Anywho, have a good one. I'll see you back here next time. If you have any questions, feel free to email me or swing into an office hour. Have a good one.